Hi everyone. Welcome to Young Academy. And today we are thinking of the IGCSE students right now that are actually going through their chemistry exam. Especially for chemistry IGCSE students right now, you should have taken your paper 4 and you should be going to take your paper 6 coming very soon, which is this week. So today we're going to look at one of the revision. But even if you're not taking exam this term, you can just follow us through. So let's jump straight in. Okay, so today we are looking at paper 6, alternative to practical for chemistry, February-March 2024. So the time limit is 1 hour, so we will try our best to finish this paper in 1 hour. Let's see how we do. Okay, so as we can see, I have already went through this paper, but we will discuss it together as well. So let me just delete some of these. Okay, this one we shifted. Wait, how to? Okay, all right. So in our first question, we are looking at experiment. Obviously, this is an experiment paper. Okay, so question 1, calcium carbonate is an insoluble solid. Calcium carbonate can be made by adding excess aqueous calcium chloride to aqueous sodium carbonate. So normally what I like to do is I like to write down the formula of whatever things that they list out in the question, because sometimes they write it in words. But in this case, the question has already written it out for us. So we can just look at the equation from the question. So we have calcium chloride, CaCl2, and then sodium carbonate, turning into calcium carbonate plus sodium chloride. So a student makes a sample. The first two are shown. So step 1 is they add excess aqueous calcium chloride to aqueous sodium chloride. Sodium carbonate. Yeah, it's over here, sodium carbonate. And as usual, I already forgot. I don't know if you students forget, but I already forgot. So what I do is I write out the symbol here one more time to help me remember. And then in step 2, they just stir the mixture. So let's look at number A. Name the item of apparatus labeled A. So especially for exam students, right? You should have a list of all the chemical chemistry lab apparatus, the stuff that we use in the lab, all drawn out and labeled nicely in your study notes. And what I recommend is students have a special notes for paper 6, because the stuff that they ask in paper 6 is different, mainly different from paper 4 and paper 2. Some stuff, yes. Okay, so this one, if you have your list, you should know that this rod is glass rod, or what we call stirring rod. So you just write the name in and it's that easy. Okay, you get the marks. Then in part B, suggest why the mixture is stirred in step 2. So, okay, it sounds like a very ridiculous question, but actually the answer is just to mix the reactants together. So I already looked through this exam beforehand, and I tried it out myself. So you just need to write the word mix. All right, I can show you the answer as well. The answer is here. So as long as you have the word mix, the substances together, or mix, write out their name, calcium chloride and sodium carbonate together. As long as you have the word mix, you get the marks. All right, let's move on. After step 2, the student filters the mixture to remove the solid calcium carbonate formed and collect the filtrate. Draw a labeled diagram to show the apparatus. So they want us to draw the setup that we use to filter, because they literally give us the word filter. So we just draw out how we normally filter things in the lab, which is with a filter funnel. And for students that have already drawn this, that you already have the list, second thing that you need to do is you need to double check whether your symbol is correct in your list of apparatus. Because for this filter paper, you have to have, okay, if you can see, there is two layers to this. There is the orange layer and the inside blue layer. So what the inside blue layer actually represents, let's label it together, all right? This inside layer represents, let's use a different color. It's not that obvious. The inside one represents the filter paper. However, the outside one, which is this orange one, is the funnel, or the full name, you can call it filter funnel. All right. So why is it important to draw it exactly like this? Because the exam has stated, the mark scheme has stated that if the students do not draw this, it's essentially like the student is using the funnel without the filter paper. And if you have tried doing the experiment without the filter paper, you would know that it's useless. Everything that dissolves in the water will just flow right through. Or like almost everything, especially small stones and whatever, all will flow through. So the whole point of the filter paper is to block out all the solids, the insoluble stuff in chemistry. So make sure you have this inside one and the outside one to get this mark. All right. And then on top of that, you need to draw the residue and the filtrate that went through. And because they said draw a labeled diagram, so you have to make sure to label the top part residue and the bottom part filtrate. And then if you want to be complete, you can write what it will be stuck at the residue and what will flow through as a filtrate. And just one moment on top of that, how do we know who flows through the filter funnel and who does not? How we know is we look on top. There's two ways to look. Number one is you look at the table where they teach the soluble and insoluble salts, but that's a bit troublesome. There's a faster way to do it here, which is we scroll up and we look. The question already labeled it for us. AQ means aqueous, means they dissolve in water. S means solid, means they are insoluble in water, because before the experiment, there is already water. So if it comes out as a solid, it means that it did not dissolve in water. Because if this calcium carbonate dissolved in water, it would not be S behind, it would be AQ, meaning that it dissolved in water. I guess it's clear. All right. So that's that. So yes, that is why we label this calcium carbonate, because this is the only insoluble thing, and then the filtrate. And just this does not include in the mark scheme. As long as you draw this and label residue and filtrate, you should get the marks, all right? But to be exact, make sure to draw this calcium chloride here, because the question says it's in excess. Excess means you have extra. That means some of it will not be reacted. So it will flow down together because there is it didn't react. Okay, all right, let's move on. For question D, the solid calcium carbonate obtained by filtration is not pure. Identify one substance other than water, which is mixed with the calcium carbonate, which makes it impure. So this actually is based on the previous one here, okay? Oh, sorry, obtained by filtration. So what we get, so, okay, if you get blur like me, you can just write on top here. So calcium carbonate, if we write it out, is CaCO3. So if we look up here, this CaCO3, they say that we obtain from filtration, which is this part here. It's not pure. Why? Because filter is not perfect. A certain percentage of it will get stuck on top here. Who will get stuck on top? NaCl and CaCl2. There definitely will be a small percentage that did not flow through. That is like sticking with the CaCO3. All right. So let's see if the answer accepts both. Yes, they do accept both. So as long as the students write either one of it, you would get the marks. All right. Okay, then we go down to the next one. Describe how the substance you have identified in D1 can be removed from the calcium carbonate. So this one is a specific step. All right, so students can actually copy this. This is like one of the things you all can copy into your paper 6 notes, which is you pour more water through the residue in the funnel, right? As long as you have the meaning of this, like another way to say it is like pour extra water. Instead of more, you write extra through the funnel or into the funnel, right? Maybe you didn't write to the residue. It's also fine. As long as you flow more water, the water will, after a certain time, it will definitely carry away all the extra NaCl or CaCl2 from the filter funnel down into the filtrate side or into the conical flask. So that is that. Hope you understand. All right. And then, okay, so originally the question is like that, right? So let's read the question first. Next question. Describe a test the student can do on the filtrate obtained in C. So what is that? Filtrate. Okay, so that means it's our NaCl and our CaCl2 because that's the filtrate, right? And they say recording according to question C. So it's this. Then let's continue. To show that the calcium chloride is used in excess. Okay, let's just double check. Was it CaCl that was used in? Yes, yes. It was used in excess. And if you want to be exact, what you can do is actually you write an excess here. So you make sure that you don't jumble them up during the exam. Okay. Give the result the student obtains if the calcium chloride is in excess. So basically, they just want us to prove that calcium chloride, CaCl2, is down here because only when it is in excess will it be able to flow down. If it was not in excess, it wouldn't be flowing down. It would just disappear all around because all of it would have been reacted. Anyway, CaCl. So let's ask ourselves, which one can we test? So I actually have this other test. Okay, so in paper 6, you can refer to the back. All the different tests are here. All right, anions, test for aqueous cations, gases, and metal ions, flame tests. All right, so yeah, in case you are not 100% sure, do flip behind to check. All right, so anyway, we want to prove that CaCl2 is there. So there's two ways to prove. Either we prove by using Ca2 plus to prove that it's there, or we can prove by using the Cl minus, the chloride ion. So let's see in the test here, right? The test which you can flip to the back of your paper, which one is available. So first of all, I see chloride here. There is a test to test for chloride. So let's see. We test with this, and then we should get this result. So they want us to prove that it's there. So we should get a positive result. But if ever the question asks the opposite, like prove that it is not there, then we have to say it will not produce a white precipitate. But in this case, we want to prove that it's there. So we write white precipitate. The second choice is we can do with calcium. And so happen there is a test with calcium as well. So this one would be much better, which is using the sodium hydroxide to test on it. Because if we use this aqueous ammonia, it is no precipitate. I mean, it's fine as well, but this one would be a lot more accurate using sodium hydroxide. So try to stay away from this, or like when you see a dash, obviously it doesn't exist, the steps, right? So yeah, but we can also use this. I think it should be fine. That means aqueous ammonia, and then we get no precipitate. So anyway, let's look back here. So yes, let you see this is from the answer, by the way. So they say that you can test for carbonate ions. Like you see, they say add dilute hydrochloric acid. So let's double check. Sorry, one moment. Carbonate ions. One moment. Ah, yeah, here. Carbonate. Oh, wait, hold up a minute. So we can prove that they are not there. So we can prove that the carbonate ions are not there. All right. Oh, yes, I forgot. So looking back at earlier, we cannot use Cl minus to prove it because whether we have this CaCl2 here, the Cl will be with the product, which is the NaCl. That one we'll definitely have. So we cannot use Cl to prove it because Cl exists in the NaCl, it is also found here. So it's not a valid proof if we use Cl because it's already in the product. All right, so we have to use something that is not in the product. So what should not be coming out? So first of all, this carbonate should not be flowing down because they said filtrate. Carbonate definitely will be stuck up here. So we can prove that carbonate is not there. All right, because as long as we prove carbonate is not there, that means that all the carbonate has finished reacting. Because in an experiment, in a reaction, there can only be one of it in excess. The other one has to be a limiting normally, all right? Unless we measure exactly how many moles of A react with how many moles of B. If not, normally there definitely is an excess. So can either prove that carbonate is not there, then we prove that carbonate is the limiting, which is this thing is the limiting. So if we prove that this thing is the limiting, that just default proves that this is the excess. Or what we can do is we prove that calcium also. We can also use calcium. Because calcium definitely will be flowing down if it is in excess because CaCl2. And this Ca will definitely be stuck on top here because it's the insoluble. So if it would come down here, that means it's coming down together with the CaCl. So we can either prove it with Ca as well. So you just copy the test like the Ca2 plus test from here, just copy it over, or you can copy the carbonate test, but you have to give a negative result saying that there's no effervescence. All right, so let's move on. So that's our first question. Now let's move on to our second question. All right, so this one looks like there's a lot of words. So don't panic if you see this. Let's just read it slowly. A student investigates the reaction between aqueous sodium carbonate and two different solutions of dilute hydrochloric acid. So normally what I do, the first thing is I write it down. Sodium carbonate, Na2CO3. Because CO3 is the charge of CO3 is 2 minus, Na is plus. Two different solutions, dilute hydrochloric acid is HCl. So we just write it down here and then we move on. The flask and burette, I actually wrote it after reading the bottom part. So let's just continue reading together. Rinse a burette with distilled water. See, so they already tell us it's a burette. And normally in chemistry, when we use a burette, it will be titration. All right, so let's continue reading. So rinse it with distilled water and then with dilute hydrochloric acid. So normally we do this to make sure 100% we are flushing out the extra leftover water inside the burette. Why? Because it is dilute hydrochloric acid. Dilute hydrochloric acid means it's a weaker version of hydrochloric acid. That means we mixed it with water. The problem is when we have water in the burette itself, it will affect the concentration of hydrochloric acid. Why? Because the amount in the burette of the hydrochloric acid is already very little. So if you just have a little bit more of water inside, it will affect the concentration and then the experiment will not be accurate. All right. I think they asked it down there as well. Like, why do we rinse it with hydrochloric acid? But let's just move on first. Rinse a conical flask with distilled water. So that's the bottom one. So if you all have drawn, it's something like that. There's like the burette on top and you drop it drip by drip into the conical flask. So now we are rinsing the conical flask below. So let's continue reading. Fill the burette with dilute hydrochloric acid A. Okay, run some of the dilute hydrochloric acid out of the burette so that the level is on the burette scale because sometimes it starts here. So sometimes we fill it up beyond the 50, that means more than 50. So we want to lower it down until it's exactly 50 or whatever is the maximum on the burette so that our experiment is accurate. Because if our measurement starts from above the 50 and there's like no reading on top, we cannot get an accurate measurement. Okay, it's not exact. So let's continue reading. Record the initial burette reading, normally 50 cm cube, or you would cml. Use the measuring cylinder to pour 25 cm cube of the sodium carbonate into the conical flask. And then add 5 drops of methyl orange. Why we use methyl orange here? Like, why do we not use universal indicator? If they ever ask this, all right, extra tip for all of you, is because universal indicator has too many color changes between the different pH values, whereas methyl orange is just two. It either shows one color when it is acid or another color when it is alkali. All right, so that's why we use methyl orange or any other indicator that only has two colors. That means they will not change color all the time. Okay, so let's continue. And then stand the conical flask on a white tile. Okay, so this white tile is also actually very important because what we are doing in this experiment is we are observing the color. We want to see at the exact moment, like how much cm cube of this, the one that we put in the burette is the acid that we drop, it will turn it into alkali. So if we use like a different a tile, the tile means something at the bottom here. All right. It must be white. Why? Because normally the tables in the science lab is wood. I don't know about your school, but based on all the old schools that I went to, the school laboratory, sometimes it's wood, sometimes it's painted with some gray paint, right? So it's not accurate if we look from here or from the side, right? And then the table color will affect it. So we purposely put a white color so that we can see the color change clearly. Okay, I think that's clear enough. Let's move on. Slowly add hydrochloric acid from A to the conical flask while swirling the flask so that we see the color change immediately. That's why we swirl it. Basically, if anyone doesn't know, swirling means mixing it. Record the final burette reading. Okay, so nothing else. So it's a very standard titration experiment. So now there's experiment 2. So, okay, you can pause the video and read slowly. All right. But we are going to read it fast. All right. If you pay attention, the first part here, they no longer wash the burette. They just refill it with hydrochloric acid. Why? Because it's sort of like this experiment 2, they're assuming that you continue it from experiment 1. So the burette is already filled with HCl, hydrochloric acid. So we don't need to wash it because it's already pure HCl inside. We just top up until it goes back to 50 so that we can have our measurement, our new measurement. Okay, and then we empty the conical flask, this one we empty it, and we rinse it with distilled water. All right, use the measuring cylinder to pour 25 cm cube. So we are pouring back a new sodium carbonate inside. So you just pay attention. This one is sodium carbonate. This is also sodium carbonate. So both is the same. So there's no change here, except that here we use thymophthalate instead of methyl orange. So please make sure before you all do this, you all have the colors of the methyl orange and the thymophthalate indicator. Stand the conical flask on a white tile. So again, it's a white tile, right? Slowly add hydrochloric acid A, swirling until it becomes colorless. Record. So this colorless is when it turns acidic, but for thymophthalate. Whereas for methyl orange, it turns orange when it is acidic. So just, it's not different. It's just that the indicator is different. And then in experiment 3, we repeat experiment 1, but using hydrochloric acid B. So why is it like, some students might be confused. So the first thing is you need to understand what dilute means. Dilute means you are mixing hydrochloric acid with water. So when we say mix with water, there's different ways to mix it. You can mix 75% acid 25% water, or you can do like 50% acid, 50% water, and so on and so forth. Like the level of mixing with water can be very different. So what it probably means is dilute hydrochloric acid B is a different mix of water and acid as compared to A. We don't know which one is more concentrated and less concentrated, but we know that they are two different concentrations. Let's continue on. I hope you can get that. All right. Anything else? You can just leave a comment down below. Okay, let's look at the question now. So the first question is just a reading. So just make sure that this one is going downwards. This one is going downwards. So when you count, you must count from up to down. So like this one here is 26.2. And also another tip is you count how many spaces in between 1 and 2. So if you like look carefully like that and like that, there is 10 spaces. So 10 spaces, then you take 2 minus 1 and then you divide by 10. Then you get every single line going down is 0.1. All right. And then I think everyone should know how to count all this, right? So just put in the value, but there's a trap here, all right? Normally, initial reading, we write it at the top. Final reading, we write at the bottom, right? But here they purposely switch it up. The top here is final, the bottom is initial. So make sure when you fill it in, you fill it in accordingly. Don't accidentally fill the initial at the top. They will minus your marks, all right? If the student makes that mistake. And then the last one is the volume of hydrochloric acid added. So this is quite simple. You'll just use your calculator, take the final minus the initial. You would get your answer. So you can check if you all get this answer, all right? You can pause the video, slowly try it by yourself. I don't think it should take that long. And then let's continue. So state which solution of dilute hydrochloric acid, A or B, is more concentrated. So if it's more concentrated, then you don't need as much, right? You just need a lesser amount and it would already have turned into acid, right? That means we would need less. So you look at A and B. So now is the time we have to remember. Experiment 1 and experiment 3 is where we do the exact same. That means we have the same indicator and the same, the different type of acid, which is A and B, but the same type of indicator, because we can see from, I even labeled it the first time I did this, like this acid A using methyl orange, this acid A using thymophthalate, and this B using methyl. So it's only a fair comparison. If we want to compare A and B, is 1 and 3, because the indicator is the same. Because we can see from these two, experiment 1 and experiment 2, that when we change indicator, the amount of acid needed is different as well. So now let's look at comparison between A and B, which is 1 and 3. Obviously, A uses less, so it is more concentrated. So you just say A, and then the explanation. Okay, this one you have to pay attention. Sometimes they say explain your answer using the values in the table, or like referring to the table 2.1. Then you have to make sure you state the results, because experiment 3 uses 38.1 cm cube and because experiment 1 uses 25.4 cm cube. Like you have to list out values if. But in this question, they didn't say you must use like the table or like the readings from the table or anything like that. So we just give a general explanation. We just say that in experiment 1, or when we use that, because the question say is when we use A or B. So we just say when we use dilute hydrochloric acid A, the volume of the acid needed is lesser compared to when we use B. I think it's quite clear, all right? All right, so y'all can just fill in the answers by yourself. Okay, maybe we can just try typing together, all right? Because when dilute hydrochloric acid A is used, it requires less volume compared when using it's very basic, all right? Hydrochloric acid B. So yeah, just write that in, you get your marks. Let's continue. Next question. Deduce how many times more concentrated this hydrochloric acid is than the other. So they didn't tell you A or B, which one. Okay, if not, we can just look at down here to say our answer here. But I think it's easy enough. So this one, we just use the normal formula in math. So you need to know a little bit of math when we calculate probability. The new value divide by the original value. All right, so you will get 1.5 times. So yeah, here we use a math formula to do this. All right, so remember it's new value divided by original value. Why? Because they want the number of times, but if they want the percentage, like how much higher in terms of percentage, then we just take this times 100%. But I'm sure all of you have learned this in math already. All right, so yeah, let's move on. Okay, C1. Compare the volume of dilute hydrochloric acid A compared to used in experiment 1 compared to experiment 2. So they just asked us to compare. They didn't say anything else. So what we do is we just compare. We just, like you just scroll up here. What's the first thing you see between experiment 1 and experiment 2? Clearly, experiment 1 uses a larger volume. So we just throw that down there. Experiment 1 uses a larger volume of dilute hydrochloric acid compared to experiment 2. All right. But if you look here, that is 2 marks. So maybe we just say clearly by how much of a factor. So again, we use the new over original. And if you do the new over original, 25.4 divide by 12.7, you please double check it with your calculator. It equals 2. Or it's almost around 2. It's like 1.9 something or 2 point something. It's very near to 2. So we can say it's around, wait, I think it's exactly 2. All right, so I'm going to double check it here. You'll double check it as well. 25.4 divided by 12.7. Yeah, it's an exact 2, okay? Exactly 2 times more. So next time, if you'll see this type of questions, don't worry if they ever ask you to like compare the factor. Normally, it's a whole number, or even if it's not, it's like 1.5. You shouldn't be getting very weird numbers like 1.765 or that kind of number. Let's move on. The third one, deduce the volume of dilute hydrochloric acid B required to reach the endpoint if experiment 3 is repeated using thymophthalate. So you see up here, once we switch from like methyl orange to thymophthalate, the amount needed divide by half. Do you see? So that's why if you can do C1, there's a high chance you can do C2. So yeah, try not to miss any questions. How to do that? Do a lot more past years. Okay, anyway, so since we know there is a divide by 2 type of relationship, we just take this 38.1 because that's the B concentration. We divide it by half and that's our answer because it's just a 2 marks. But do take note, if the student forgets to write this unit, cm cubed, they will minus 1 mark. That means out of 2 marks, you only get 1 mark. And for the answers, you can either write 19.05 because that's the exact dividing, or even if you round it up to 19.1, you can get the marks. But normally, I would recommend if it's just 2 decimals, just write all of it. Try not to round up because sometimes they might not accept the rounded up answer. Then, I mean, it's very less. Normally, they accept the rounded up answer, but just to be safe, you know? Okay, let's move on. D. At the start of experiment 3, the burette is rinsed with distilled water and then with dilute hydrochloric acid. B. Okay, yes, because experiment 3, like, okay, let's just scroll up one more time. Because in experiment 3 is a, like, okay, this is what I was explaining earlier. When we say dilute hydrochloric acid B, like the name is already the exact same. Dilute hydrochloric acid A and dilute hydrochloric acid B. So what is the other thing, the only other thing that can be different? the concentration. That means how many percentage of water you mix it with. That's the only thing that can be different. That's why students have to be able to assume that. So what's the important thing here? Students need to know what diluted means. If a student doesn't know what diluted means, they would think that A and B are the same thing, and then they would not be able to answer the question. So that's why understanding the meaning of the word diluted is very important for at least this exam question. Okay. So here, so why must we rinse it with water? Because it's a different concentration. So obviously we rinse it with water and then we put in our new dilute hydrochloric acid B. All right. So what do we want to wash out? So you just think, okay, so even if you all didn't get it, you can just think it like that. What was in the burette before experiment 3? So if you scroll up, all right, I did a small little drawing by myself. So I also highly recommend you draw this. Okay, it doesn't add marks to your question, but it helps you imagine the question much clearer. At least for me, it does. So you see here, I write HCl in the burette, and clearly at first it's HClA. So we are trying to wash HClA out of the burette because that's the only thing that's in the burette, okay? So I won't explain too much of that. So you just write dilute hydrochloric acid A, but please write this in full name in the exam, okay? Don't write short form, huh? All right. Then let's go to question 2. Describe how the result of titration would change if the burette was not rinsed with dilute hydrochloric acid B. So because we have found that dilute hydrochloric acid A is more concentrated, right? So that means that if we didn't rinse it properly, then this B, the amount we need is lesser because it increases the concentration. Because when you have a little bit of A mixed with B, I know it's just a little bit, but it will still increase the concentration because A is a stronger acid, as we have seen here. It uses a lesser amount. Anyway, I'm repeating already. So, all right, it will cause the amount of wait, one moment. How would it change? Wait, let's just double check the answer. D2. Okay. Oh, wait, let me think for a while. If the burette was not rinsed with hydrogen. Oh, sorry. I read the question wrongly. The question is asking how would it change if we did not rinse it with hydrochloric acid B after it had been rinsed with water? So that means now we are saying that the water stays inside the burette. So it will lower the concentration, right? Lower concentration means you need a larger volume to cause it to turn to acid. So it's increased. My apologies. All right. So learn from my mistake here. Finish reading the question first. All right. Don't just write the answer before reading the question carefully. All right. So it's had not been rinsed with water. All right. Not to, yeah. What I understood was if we just like we just flush out all the hydrochloric acid A and then we don't rinse with water, we just pour in the hydrochloric acid B. Anyway, that's a misunderstanding. Let's just move on to the next question. Explain why the conical flask is not rinsed with aqueous sodium carbonate after it is rinsed with water. Okay, so let's just read that again. I read it too fast. Why the conical flask is not rinsed with sodium carbonate after it is rinsed with water. Okay, because this one is very interesting, all right? This is another very important thing that students can copy into their paper 6 notes. Because, all right, let's go up to our drawing here. For this burette, there is a going in place where we can put in the liquid, and there is a going out place. So at any time, if we pour extra, we can just let it out. But if it is in this conical flask, there is a going in, but there is no going out. So therefore, if we just rinse it with that sodium carbonate, a lot of it will be stuck inside. Okay, so recap, all right, we only rinse it with like the acid or whatever we use in the experiment if it is a burette. because in all the apparatus that we have, only burette has a going in and coming out. Whereas, like for example, this flask here and a lot of other things, there's only a going in, but there's no coming out. So in that case, it's better to just maybe let the water dry first or like wipe it dry first before we pour it in if we really want to make sure there's no water left inside. Okay. Yeah. So that is why we um, rinse the burette with the acid, but we don't rinse the conical flask with the whatever else, in this case, sodium carbonate, right? Because it will increase the volume of sodium carbonate and cause the accuracy. And another thing is, okay, this one here, if we read, so in this question, they want 25 cm cube. It must be exact. All right. And on top of that, another reason why it's not so important to flush out all the water, the small drops of water, is because this is aqueous sodium carbonate. Aqueous sodium carbonate. It is not a diluted version. So the effect is rather minimal as well. When will the effect of water, like the leftover water droplets, be big? When your thing is a diluted thing. For example, the one in our burette. Then the effect will be strong. But if it's already a strong and concentrated one, the effect will not be too big. Anyway, let's move on. So increase the volume of sodium carbonate and cause inaccuracy for the 25 cm cube. Let's see if the answer requires us to write the 25 cm cube, D3. So D3 here increases the volume. Okay, so good news. Students would still get the marks even if they didn't write the 25. But just write to be safe, because you never know. One day they might want us to write the 25. So it's better to train for the worst. Okay, let's continue. Explain why a white tile so that the color change is more obvious. Basically what I was explaining earlier when we were reading the question. All right. So just a heads up, students, if you don't know this, please copy it. Like all these things is things that you need to know about the titration experiment. All right, there's like different questions they can ask us in the paper 6. This is one of it. So copy all this down. Important notes. All right, copy it under one experiment called titration. Anyway, let's continue. Describe the effect on the result of warming the aqueous sodium carbonate. Okay, so warming before carrying out the titration. Explain your answer. Okay, so let's read it one more time. This one, I think we have to be extra careful. Let's just, can I delete this? Yes. All right. Describe the result of warming the aqueous sodium carbonate used in experiment 1 before carrying out. Okay. They want the aqueous carbonate used in experiment 1. So it's the volume that we are looking at. Always think the first thing you think about is like, what unit are you talking about? So in this case, the unit we are talking about is the amount. So when we talk about amount, it will not change, because if you pay attention, the increase of temperature will increase the rate of reaction. That means it will happen faster. But it doesn't mean that a higher percentage will react. It's just that it goes faster. That's all it means. So based on the amount used, there is no change, or you can say no effect. Either you write no change or no effect, you get the answer. Okay, why? Exactly what I just said. Because the higher temperature will make the reaction faster, but it will not change the amount needed. All right, so that is the answer. I hope everyone is clear. All right, if not, you need to revise your rate of reaction. Or like, what even is the meaning of the word rate of reaction? Rate means how fast. Especially those that learn physics, you would know, huh? Okay, anyway, third question. So let's, okay, hopefully we are still on time, all right? We need to try to finish in the 1 hour mark. A student tests 2 substances, solid C and D. Solid C is ammonium iodide. And as I always tell you all, write out the formula somewhere beside, somewhere nearby. Okay, NH4I. The student dissolves solid C in water to form solution C. If I were you, I'd double check my solubility table. That means which salts are soluble and which isn't, just to double check. Um, okay, and then it's divided into 3 equal portions, the expected observation. So to the first one, the student adds 1 cm of dilute nitric acid followed by a few drops of aqueous barium nitrate. So if you read this, especially when we add 2 different things, there's a high chance that it comes from the back of the paper, one of the tests here. So let's look at it again. Dilute nitric acid and barium nitrate. So I even wrote up the BaNO3 here. So let's see which test uses nitric acid and barium nitrate. Nitric acid, barium nitrate. I just repeat it one more time. So here is nitric acid, but here is not barium nitrate. So it's not what we are looking for. Here, we found it. Nitric acid and then barium nitrate. But sometimes, unless you are a student that has memorized everything and you're 100%, only this one have it. But if you're checking, check everything else. Because sometimes there's more than one that have that test. Sometimes, all right? So let's just scroll down here. So this is everything sodium hydroxide, everything ammonia. So it definitely has nothing to do with this. So therefore, we can conclude that this is the only one. But I'm just saying, pay attention, because sometimes, especially for like sodium hydroxide, it can be something down here, or it can be something down like up here, because this one also uses sodium hydroxide. So especially when you're looking at sodium hydroxide, be extra careful. All right, so we come back here. So, all right, so we know that this is the test, nitric acid, barium nitrate. So we get an SO4 2 minus. All right, so we come back here. We look at the thing that is being tested. Does it have SO4 2 minus? No, right? So if it doesn't have, it should be a negative. So here is a white precipitate. So here we should say no change, all right, or no precipitate form, all right? Basically, we write the negative result. Then for part B, to the second portion, adds 1 nitric acid, silver nitrate. So nitric acid, silver nitrate. So it's nitric acid, silver nitrate. So if you pay attention, this is all for the group 7, the chlorine, bromine, and iodine. So the one that we use here has iodine, I minus. So therefore, there will be a positive. So what is the result? It's a yellow precipitate. So we just fill it in because this is the iodide one. All right, so iodide uses this one, so yellow. So we just fill it in, yellow precipitate. Okay, then to C, question C. Okay, let's read the question first. To the third portion of solution C, the student adds an excess of sodium hydroxide, NaOH. So observations, no change. Why? So let's look. So if we look over here, you have to, like I was just saying, right? Sodium hydroxide is in a lot of places. So let's look through all of it. Sodium hydroxide, first of all, is here. So this one is for the cation, or what we call the positive. And we look back here, the positive is NH4 plus. So let's look back here. Is there what sodium hydroxide with NH4 plus? Yes, we have it. Ammonia produced on warming. Okay, so this word warming, students have to understand this, because if students just memorize this question might cause them to fall, all right, to make a mistake. Warming means heating up, or at least some form of increase in temperature. But here, this is where students have to pay extra attention, all right? So when you study this table, make sure you understand what they mean. So coming back here, right? Read the question one more time carefully. Did any part in the question say that we heat it up, warm it up, or even increase the temperature? They didn't. So if they didn't, means there is no change. We only get the change when the temperature increases. I hope all students are clear on that. Okay, this is a very tricky question, all right? Especially for students that only memorize, be careful here, all right? And for C2, the student warms the product from C1. So you see, even if the student didn't actually notice it, if you read this second half of the question, actually they're giving you a hint. It's like, pay attention, warming. So like, then when you warm, then you will get the ammonia. And then they say, and test any of the gas. So like how to test the gas. So you see the ammonia. So how do we test ammonia? You scroll down, it turns damn red litmus paper blue. So you just throw it inside and that's the answer. Just throw it inside here. Turns damn red litmus paper blue. So you just throw it inside here and you can get the marks. All right, so I just come over here. Make sure you write this answer in. All right, pause the video if you need to, and then I will move on. Okay, and then we have solid D, donkey. So first test, do a flame test, we get yellow color. So again, we just open here. Which flame test gives us yellow color? Sodium. Is there any other yellow color? No. Everything else is not yellow. So it has to be Na+. So please write beside here Na+ so that you are clear later on when we do a question. Test 2, gently heat half of the remaining, hold a strip of anhydrous cobalt 2 chloride. So if you all have read this test is not here. Yes, it's not here, okay? But you all have to look at the chapter where we learn about water. So that in the chapter where we learn about water, there's one test that tests water. How to test the presence of water or water vapor is by using this anhydrous cobalt 2 chloride. All right, and because steam is given off, like even if you didn't catch that, you read this, steam is given off, and steam can only be one thing, water vapor in gas form. All right, and condensation forms, like it's very obvious really, all right? And then the anhydrous cobalt 2 changes color. So here they didn't even test us what color changes to what color. They just tell that it changes color. So it's clearly telling us that water is here. So you just write in H2O. All right, just write it beside. That means we know that there's H2O inside this solid donkey. And then let's move on. Okay, all right. Let's look at test 3 now. So test 3 says it dissolves the remaining solid D in water to form solution D. To the first portion of solution D, add aqueous ammonia dropwise until in excess. And then we get green precipitate, which is insoluble in excess. All right, so let's look at our test. Which one gives us a green precipitate? And then let's look back here, insoluble in excess. All right, so green precipitate insoluble in excess, is iron 2+. So we just write Fe2+ here. Fe2+. All right, and then we look at test 4. Test 4, to the second portion of solution D, add aluminium foil and aqueous sodium hydroxide. So I think aluminium foil is there's only one place where we use it in a test. So aluminium foil, the only place we use it is this one. So it's nitrate. So we should have ammonia produced. But let's look here. Yes, there is a precipitate, but it says the red litmus paper remains red. So you see here, if we get ammonia from this one, what the ammonia should do is turns the red litmus paper blue. But it says it remains red, so therefore there is no nitrate. This test is proof that there is no nitrate. Let's move on to test 5. To the third, add dilute nitric acid or nitric acid. Bubble any gas and we get effervescence. So there's two ways to do this. So like the first way we can find is we try to find nitric acid. So like if you look here, right? If you look here, you find all the things with nitric acid, but you see here, they only add nitric acid. They didn't add anything else. So you see here, nitric acid plus silver nitrate. So it's out because it's using two things, right? And then here also is using two things, nitric acid. And just to double check, we can also check down here, anywhere we use nitric acid. No, you can pause and look through by yourself, but it's no. So what is the answer? The answer is we can also find this observation here, effervescence. So we try to look here, where do we have effervescence in these two tables of tests here? There's only one place we see effervescence. which is here. So that comes us to find, you see, this one is dilute acid. So students must be clear for this test to test carbonate. It can be any acid as long as they are dilute acid. That's why they write here dilute acid. They didn't specially write dilute nitric acid or dilute sulfuric acid or anything like that. And on top of that, this is the only one that has effervescence. So clearly it has carbonate. So here they say the effervescence, lime water becomes milky. So let's scroll down. The one that lime water becomes milky proves that there is carbon dioxide, is a positive for carbon dioxide. So it proves to us that there's CO3 2 minus. Now let's come over here. State the final color of cobalt 2 chloride paper in test 2. So test 2 here. So here they just say changes color because down there they want to ask us. So this one you have to look back at the water chapter. When there's water, especially for cobalt 2 chloride, it will turn pink. This one you have to refer to your notes, all right? And then the next one is this one here. State what ion observations in test 4 is not present. So in test 4, it showed us that it is not NO3 minus. So either you write NO3 minus or you write nitrate with a ATE at the back. All right, make sure it's the right, the behind three word, the letters must be correct. Next, identify the gas produced in test 5. So in test 5. Okay, but this one is very tricky. They are not asking the ion that is produced. They're asking the gas that is produced. So like, what gas turns lime water milky? Clearly carbon dioxide. So they want the gas produced, not the ion. So be very careful. See what the question wants. And then identify the 3 ions in solid D. 3 marks. So that means we have to list out 3 different answers to get us the 3 marks. So we just write Na plus, Fe2 plus. Do we write H2O? Let's look at the question one time. They say the ion. Ion is things with charge. H2O is not something with charge, so we don't write H2O. So Fe2 plus, Na plus, and also CO3 2 minus. Just throw it in and you get your marks. Finally, we are at our last question, all right? So when excess dilute sulfuric acid, which is this one here, is added to solid zinc, all right? Hydrogen gas and zinc sulfate are made. Plan an experiment to show that copper is a catalyst for this reaction. So they even tell us that copper is a catalyst. Your plan should include how the results of the experiment will show that copper is a catalyst. Okay, so students should have learned this for their paper 4. This is something that they like to ask in paper 4 as well, because copper, one of the thing in the definition for catalyst is they themselves do not take part in the reaction. All right, so how do we prove it is we prove the either the mass or the volume, but because here copper clearly is going to be a solid. So we prove that the mass of the copper before the experiment and the mass of the copper after the experiment is the same. That's the most important thing we need to prove. That's what the question is asking. You are provided with zinc powder, dilute sulfuric acid, which is this, right? Copper powder. Okay, so that means it's in copper powder form, and common laboratory apparatus. All right. So normally, we start our experiment. The first thing we think about is like the 3 different variables we have: manipulated, responding, and fixed variable. So our manipulated variable is actually, for this experiment, there's no manipulated. I'm sorry. That was more for physics. But for chemistry, we just need to give the steps. So let's just double check. It's 6 marks, right? So we need to make sure to write at least 6 different steps or like precautions or whatnot. All right. So, and also we must make sure to write all the different lab apparatus that we need. So clearly, the first thing that we need to do, the big idea, right, is to react the zinc with the sulfuric acid in the presence of the copper, right? Okay, so, all right. So we prepare did they say who is in excess? Oh, yes, they did. Excess dilute sulfuric acid. Okay, so that means we can prepare a lot of dilute sulfuric acid, all right? And then our solid zinc, We can just add a little bit of it. And then how do we know that the reaction is happening or has already started happening with this hydrogen? Okay, so we have to say somewhere that we observe the gas bubbles. Once there's gas bubble, means there's hydrogen gas produced. Okay, and then let's think about it here. Is everything here soluble in water? Most of it, except zinc powder. So that's why we must use sulfuric acid. So actually the question told us a important tip here. Because if we don't finish up our zinc, then it will be stuck when we do the filtration, which is the, I think, first or second question in this paper. And then we cannot really, it will make our test inaccurate. We have to make sure that all the zinc is disappeared so that we can measure just the copper by itself. Because if the zinc gets mixed inside, then we cannot prove our point anymore. All right, I hope everyone's clear. So let's take a look at the answer. All right. Okay, so let's just shift this answer over. Oh, one moment. Let's minimize it. Okay, so we use a metal, a way, see like here, Ne6 from here. So we just have to make sure that a known measured state or fixed. So you can either say you measure it or you give an exact volume of the dilute sulfuric acid, which is this one here. But how I like to write, right? Okay, let's put it up here. Let's see if we can type. Okay, so I'm just gonna type in point form here. Measure. So just give an amount. It doesn't as long as it's a reasonable amount. So we can go back with, like, let's say 25, but yeah, we can go with 25 cm cube of dilute sulfuric acid. Okay, how do we get this? Because on top here, dilute sulfuric acid. In case anyone is not sure of the spelling, with a measuring cylinder. Like what I always like to teach is make sure to say what do you use to measure. Don't just say measure. Using a measuring cylinder or whatnot. And then number two is, so after that, we need to measure our zinc and also we need to measure our copper. So we just say use electronic balance, oh, sorry, to measure um, something small because we want to make sure that all of the zinc has reacted. So maybe like 10 gram, 10 or 20 gram, I think it's fine, right? Of zinc powder. Why powder? Because the question told us that they give us zinc powder. All right. And then three. So here, three, they say measure the time to collect a set volume of gas. All right. Ah, okay, I see. They are doing the experiment first without the copper and then with the copper to to see the increase in the mass after we use the copper. All right. Okay. All right. So that's a even better way to do it. All right. So we say measure time. Okay, or like the time, or we can just say normally what we do is the time until there is no more effervescence, right? Until there's no more carbon dioxide produced. Then for question four, all right, we say that actually this is very weird if we follow the answer here. Normally this one, okay, and also wait, one moment before we even like measure the what and all, we say place them like, okay, place the, so this one you all can say place the dilute H2SO4 in a flask, which is where our chemical reaction will happen first. All right, test tube, or it can be a boiler. If you can see here, as long as it's any of the suitable reaction vessel, conical flask, test tube, any of it. All right, flask, and place the zinc powder into it. So like we place the zinc powder into the flask and let them react. And then number 4, only we start measuring the time. That would be a more natural way to do it. All right. Until there's no more effervescence, or you can write any of the other answers here. All right. So because we write measure the time until there's no more effervescence, we don't really need to collect the gas. But if you write like any of this, like the time required to collect 25 cm cube of gas or like 10 cm cube of gas, then you have to make sure your syringe, like you actually have your, like the conical flask like that. All right. This is if you write that. All right. And then here you place the rubber bung and then you place like the syringe like that. And then it whatever gas that comes out, it goes directly to our syringe. You get what I'm saying? But if we say we just, oh, sorry. Oh, okay. Let's just how to shift this back. Okay. But because we just say measure the time until there's no more effervescence, then we don't have to say about the syringe. All right. Now we repeat. So we say repeat the experiment, but we add copper powder. And don't just say add copper powder. Always when we add like maybe, so how much did we add? So 20 grams. So maybe we can add 10 gram of copper powder as long as it's a small amount, right? And then number 6, now we just prove that filter the copper from the solution. Okay, so we are still assuming that our solid zinc is the limiting reactant. That means it has 100% fully react. How do we know that? Because our experiment, if following what we type here, is until there's no more effervescence. So as long as there's still water inside, all right, there's still like liquid inside here, there's still extra hydrochloric acid, but there's no more effervescence, means that the reaction has fully taken place. So whatever solid left inside, it has to be copper and only copper. So that's why we filter the copper from the copper solution, from the solution. And don't take it for granted, using a filter funnel and filter paper. All right. Sometimes they will require us to say what we use. All right. And then number 7 is dry. Okay, this is very important. Dry and weigh the what's that called? Residue slash copper slash copper. All right, we have to say we dry it first and then we weigh it. All right, it's just every time when we have something like coming out of aqueous solution, we have to dry it first. All right, so this is another thing that students can write inside their paper 6 notes. And then for the number 8, all right, we measure the mass. Okay, double check. All right. Oh no, the best experiment word is compare the mass that is filtered out from the solution to the amount of copper mass included in the experiment in the maybe you can say before the experiment is repeated, which is the second time that you do. Right? And then to make it 100%, the mass of copper powder should stay or not stay the same, stay constant, we can write. All right, constant uh before and after the uh reaction, or you can write experiment like that. All right, so we need to state that um or maybe we like that is better. If the mass of copper stays before and after stays constant before, okay, then we say this proves that copper is the catalyst in the experiment. All right, so that if it doesn't change, it proves that copper is the catalyst. All right, so just write in all this extra stuff. I hope you all are clear. All right, and that is this paper. So hopefully we completed it in 1 hour. I think it's a little bit over 1 hour. All right. So I hope this has helped you in your chemistry paper 6 preparation. Um, do let me know if you have any more questions. Comment down below and see you in the next video.